writing net ionic equations for single replacement reactions takes a little bit more effort than the double replacement, but it's still one of the easier types of reactions to write. When you're looking at single replacement reactions, there are three basic types. You have a metal plus an ionic compound, you have a metal plus an acid, or you have a halogen in an ionic compound. And a single replacement reaction, again, remembering the format, is an element combined with a compound. The free element replaces one of the elements in the compound and then bonds with the remaining. So this is a typical format of single replacement. So an example, you would have calcium plus cobalt chloride, calcium replacing the cobalt, giving you cobalt metal, and then forming calcium chloride. Or a metal plus an acid, calcium plus hydrochloric acid, would give you hydrogen gas and forming calcium chloride. A halogen in an ionic compound, taking fluorine and reacting it with a compound that also contains a halogen. In this case, the fluorine will replace the chlorine and form the compound. And then you would have to go back, of course, and balance these, and you'd have to go back and balance the rest of these as well. But these are your typical single replacement reactions. Now let's turn them into net ionic equations. Don't forget, before you do any single replacement reaction, you always need to check the activity series to make sure that the reaction will actually occur. So here's our first example. We have magnesium metal added to a solution of silver nitrate. So write the formulas. Solution of silver nitrate would give us silver ions and nitrate ions. And then we go back and we look at what is going to happen. The magnesium is going to push the silver ion out, forming silver metal, and then it is going to be converted into the magnesium 2+ ion, and it will react. So if you've got your magnesium 2+ ion reacting with NO3 -1 ion, you're going to get your magnesium nitrate. That, of course, is going to be a soluble compound. So to turn this into our net ionic equation, we need to look. The magnesium would not cancel with the magnesium ion. The silver ion would not cancel with the silver metal. The only thing that's going to cancel is the nitrate ion. So if we look at what's left, we've got the magnesium metal and the silver ion on the left, forming the silver metal and the magnesium ion on the right. And this is a typical format for any metal with an ionic compound. You have the metal on the left turning into the metal ion on the right, the metal ion on the left turning into the metal on the right, and then you need to make sure you have balanced for true plus on this side and only a +1 over here, so you need to get a +2 over here. That's going to mean you need to balance your silver and your magnesium ions for charge as well as atoms. Let's look at another example. In this case, we've got our magnesium metal again, and we're reacting it with a solution of hydrochloric acid. Hydrochloric acid would be ionized. The format again for a single replacement with a metal and an acid, and again you would have to check your activity series to make sure that magnesium could replace hydrogen, but it certainly can, giving you hydrogen gas on the right, and then the compound magnesium chloride. The magnesium chloride is a soluble compound, so that would be ionized. That would be ionized on the right. If you look at your spectator ion, it's going to be the chloride ion. So if we write our net ionic equation, we've got magnesium plus the hydrogen ion being converted into hydrogen gas and the magnesium 2+ ion. So the general format, the metal went to a metal ion, the hydrogen ion went to hydrogen gas. Again, we would need to balance for charge. We've got a 2+ over here. Putting a 2 here not only balances for charge, but also balances for atoms as well. Another example is our halogen replacement. We've got chlorine gas and we're bubbling it into a solution that's an ionic compound that contains a halogen. So your chlorine gas, don't forget chlorine is diatomic. Your solution of potassium iodide, well, all potassium compounds are soluble, so that would be ions. Again, your chlorine is going to replace the iodide ion, turning it into elemental iodine and forming potassium chloride. Your potassium chloride compound would be soluble. So if you look at your spectator ion, again, it's only going to be the potassium ion. So what you've done is you've taken the elemental chlorine gas and turned it into ion, and you have taken the iodide ion and turned it into elemental iodine. And this is always the format for your single replacement of a halogen. Your elemental halogen goes to an ion, and your ion goes to the elemental hydrogen. And these are not balanced for atoms. You have a 2 you need to place and a 2 that you need to place here. Now it's balanced for atoms and charge. Another type of reaction that you will see that is similar to a single replacement is when you take an alkali or alkaline earth metal and react it with water. So if we take our sodium metal and we react it with water, again, water would not be ionized, we're going to get sodium hydroxide and hydrogen gas. Now, we don't make sodium oxide. If you looked at this as a single replacement, you might think, well, okay, I'm pushing out the hydrogen, make sodium oxide. But in fact, the sodium oxide continues to react with the water to produce the hydroxide. Again, alkali and alkaline earth metals always produce bases or hydroxides in water. Sodium hydroxide would be a soluble hydroxide, so that would be ionized. And then we would go back and look at our equation. Well, the sodium metal would not cancel with the ion, so that remains. The water is not canceled. The sodium and the hydroxide ions do not cancel, and the hydrogen remains. So this net ionic equation doesn't have any spectator ions that cancel out. We would need to go back and take some time to balance it for both charge, and we can see here that we've got a +1 and a -1 charge. That would be giving us a nice neutral charge on this side and a neutral charge here. We do have 2 hydrogens here and 1 hydrogen there, so we would have to balance our hydrogens. So if we put a 2 in front of the hydroxide to give us 4 hydrogens, balance this with a 2 to give us 4 hydrogens, we now have 2 oxygens and 2 oxygens and 1 sodium and 1 sodium. But we also have a -2 charge now with the hydroxide, which gives us a net negative charge, so we're going to have to balance that with a 2 in front of the sodium and a 2 in front of the sodium. So this balancing of these net ionic equations can sometimes be a little tricky, but with practice you'll be ready to go.